Here from mechanical. So those who joined, I'm audible properly, guys, all of you. Just for the last time, then we can start. Fine. So all of you from aerospace or anyone here from mechanical also? Fine. Okay, so here we will be starting our basically session on the fluid mechanics, and we are basically going to discuss about the fluid kinematics, right? So quickly, I will just mention the syllabus part, you know. So in a particularly fluid mechanics, we will be having the fluid statics, we'll be having the fluid statics, and then we'll be having the fluid kinematics, and then we'll be having the fluid dynamics, right? So these are the basic category in the fluid mechanics: fluid statics, fluid kinematics, fluid dynamics. Then we have the laminar flow, again through pipes and between the parallel plates, or maybe fixed and one plate is moving. And then we'll be having the turbulent flow. Then we will be having the boundary layer theory, right? And then we'll be having the dimensional analysis and similarities, right? So those are the basically major topics that we are going to cover, right? So basically in this one, in today's session, we are going to cover our major time on this fluid kinematics, right? This part we are going to cover. Now, coming to this fluid kinematics here, in the fluid, particularly fluid kinematics, first of all, what do you guys know about these fluid kinematics, right? It is a very similar concept that you might have learned in the any engineering mechanics. Let's suppose any ball is there, or any object is there which is moving with some velocity, with some acceleration, right? So in the particularly domain of solid, or any solid ball which we have covered the motion, suppose any ball is there which is moving, let's say with the velocity v, right? So in the particularly fluid context, what is the particularly what is the displacement, what is the velocity, what is the acceleration, we have to discuss in the fluid kinematics, right? Before discussing the fluid kinematics, there is a major difference between the solid mechanics and fluid mechanics, right? Anyone know about the differences of solid mechanics and fluid mechanics? See, so very quickly I will cover this. If you just consider the solid mechanics, so any object if we take, right, any object if we take, if we just placed on a surface, right, and when you just apply the force, maybe little bit amount of force, so whatever the deformation will be there, right, whatever the deformation will be there, that is a fixed deformation, because they have some property. Individual object will be having, whatever the object will be there, or maybe steel or any material will be having some kind of what, basic elasticity. Here, if you are applying the shear force, shear modulus property will be there. So with the help of that shear modulus, it is going to have fixed deformation, right? But if you just coming to this fluid mechanics, this deformation I'm talking about, this deformation is a fixed one. But in the fluid, let's suppose same object you are taking, but now it is fluid. Even you are applying little bit amount of force. If you just apply a little bit amount of force, something like this, right, we call here shear force, right? So here, because the force is applied what, parallel to the surface, so this particularly fluid will be continuously deforming. It is not going to have the fixed deformation, it is going to have the continuous deformation, and that is what we say the flow, right? So that is a major difference between the solid mechanics and fluid mechanics. Now here we will be trying to understanding this fluid or whatever the behavior of the fluid in two categories by two description. One will be Lagrangian description and the second one will be the Eulerian descriptions, right? Those are the two descriptions by means of which we gonna study this what fluid kinematics or maybe whole fluid mechanics. We gonna basically look at the fluid mechanics by two ways. One will be Lagrangian point of view, second will be Eulerian point of view, right? What is a Lagrangian description? Just now focus on this. So in this first Lagrangian description, when you try to focus your attention, right, by giving a very simple example of pull table, right, this one. Now, do not focus on this whatever the definition is there right now or whatever the description. You just focus on this pull table, billiard board, whatever the game is there, right? So here, what you're understanding, individual ball is there, right? This is ball, this is also ball, this is also ball. So we can able to trace. Suppose you are hitting the ball with this stick, so you can analyze. You can see the motion, right? You can see the basically whatever the motion, whatever the path that is being traveled by individual ball, right? By means this particular person can able to see what can able to trace individual ball motion, right? So that is the Lagrangian descriptions, right? So what is the meaning of Lagrangian descriptions? We are basically tracing each and every individual particles of a flow field, right? Suppose we are considering this as a flow field. So whatever the actually we don't define the flow field here in the Lagrangian, but suppose we are considering individual ball, so we are tracing what individual motion we can able to trace, right? Ball will be here, after some point of time it will be here, and then it will be here, for example. We can trace it. But now individual ball, if you're tracing, suppose this particular ball number one is taking suppose 10-second time to basically enter into this particular goal post. Second ball is there, you gonna again trace this particular particle also. This third particle also you will trace it. The fourth particle also, fifth particle also. One particle 10-second, second particle 20-second. Now here you have the pull table. Limited amount of ball is there. You can able to trace it. You can able to calculate the velocity, mean velocity, by knowing the individual ball velocity divided by number of balls. That is a very simple calculation. But in the fluid mechanics, my dear friend, you just consider the pipe flow problem. For example, the fluid is flowing in a pipe, right? This particular fluid particle will comprise of not a single fluid particle, not a 10 particles. It will be containing what? Millions and billions of fluid particles, right? Individual, whatever the individual tracing and calculating the total time for a particular single particle will be time consuming, right? So basically it is one of the tedious job in case of what fluid mechanics. It is going to be work for the solid mechanics where we have the limited amount of object, we can able to trace it. But in the fluid mechanics where the billions and million numbers of particles are there, lakhs of particles are there, tracing individual particles will take lakhs of amount of time. Suppose you're doing any experimental kind of things in your laboratory, fluid laboratory, and it is going to take what huge amount of time, right? Suppose you have the deadline to complete the particular experimental on particular study. Let's suppose 6 months is given to you, but due to tracing of individual fluid particles it will take huge amount of time, maybe 6 years also, and that is not advisable, right? So that is what the Lagrangian descriptions, right? Lagrangian description we also call control mass system, right? This thing again you will understand in the thermodynamics also. That is basically fixed mass system, fixed mass system or control mass system, right? So these are the things. Second, when you focus your attention on, suppose now you are wearing the glass and that glass containing Eulerian descriptions, right? You can look at the fluid mechanics in two ways. I told you one will be Lagrangian glass, second will be Eulerian glass. Now you are wearing the Eulerian glass and you are looking at the fluid motions, right? What is going to be happening in the Eulerian descriptions? Suppose you have the flow field like this. You have the tank. Now, for example, this is my, suppose a control volume is there. I'm just taking one control volume. This is my different control volume. This is what we have, control volume. In this control volume, what the Lagrangian said, you don't trace individual particles. Rather tracing individual particles, you just focus your attention on single position. That means you just consider one space, right? We have considered one space. Whatever the black color is there, that is my control volume. That is a fixed particular volume on which we are going to focus our attention, right? And he said that you just focus on one particular position. Let's suppose this is the position, inlet position. Infinite number of particles are passing through this segment, right? And this is also one position, that is the output section, by means of which the fluid is going out of this what control volume. So what the Lagrangian, what this Eulerian description said, that we are focusing our attention at a particular point, right? So according to him, we are focusing our attention at a point and define the velocity, displacement, and acceleration at that point. Now, some of you might be thinking, sir, I'm not getting exactly the difference between the Lagrangian description and Eulerian descriptions. No need to worry. I will give one example. Let's suppose you are basically moving in a city, right? Suppose you have, this is a city, for example. In a city, suppose we have the different positions, right? So here we have the number of, in a particular city, you know that many cars are there, right? So let's suppose the cars are moving. Basically, the cars are moving. Maybe infinite number of cars are there. I'm not saying that fixed number of cars. Any number of car you can take, right? Suppose I'm just taking 3 cars, or maybe motion of 3 cars. I'm just considering motion of 3 cars, for example. So here, what you're understanding. So in this particular city is just like a what? Velocity field. City is like a velocity field, right? Now you are focusing your attention. Suppose you have the 3 cars, car A, car B, and car C. Individual, you are sitting in a car. 3 cars are there, 3 persons are there. Suppose, for example, you are sitting in a particular car and the car is moving in a particular certain direction, right? Now, whatever the motion of the car is there, you are sitting in a car. That means you are what? Analyzing the motion of the car with respect to what? Lagrangian descriptions, right? Whatever the motion of the car will be there, the car A, whatever the motion of the car will be there, you are tracing the car motion, right? So now, so whatever the speedometer will be there, whatever the speedometer reading will be there, which is basically attached with the car, is giving you the reading of velocity at a different instant of time at different locations, right? That is nothing but the what? Lagrangian descriptions. But I would say, suppose in a city you will be having what? A speed breaker, or you'll be having what? One traffic signal. Suppose here you have the one traffic signal. Here again you will be having one traffic signal, 1 traffic signal 2. Once again you will be having traffic signal 3 here. So I'm not focusing my attention on individual 3 cars, car A, car B, car C. Suppose car B is here and car C is here. I'm not focusing our basically my attention on motion of individual car A, car B, car C. What I'm just doing, I have just defined one control volume. Okay, this is my control volume, my city. I'm not focusing my attention on different city. I'm focusing attention on what? City number X, for example. In that city, I have fixed my location of attention. That at this location, I will be focusing my attention completely. And what I'll be analyzing that whatever the number of car is there, car A will pass through this, car B will pass. See, obviously is there. Suppose you want to reach from here to here, you have to pass through the traffic signals. That means what? The car A will also pass through this location. Car B will also pass through this, and car C will also pass through this, right? Or you can consider traffic instead of traffic signal. You can consider what? Speed breaker. So definitely speed breaker. Whatever the speed breaker is there, it will be having more what? It is going to have some speed limitations. Beyond that, this particular car should not be passed through that particular location, right? So at this is whatever the what we say speed breaker. If I say velocity of the speed breaker or velocity at this traffic signal, that means what? That means what? We are looking with respect to what? Eulerian description point of view, not with respect to Lagrangian. Infinite number of cars, let them pass through this traffic signal or whatever the speed breaker is there, right? But my focus is what? At this space. My focus is not the history of the car distance, that what it has traveled from initial point to this particular point, this particular positions, right? That is the purpose of Lagrangian description, right? The purpose of the Lagrangian description is that to basically exactly trace the history of individual particles or individual car. But my focus is that what is the velocity at the speed breaker 1, speed breaker 2, and speed breaker 3. And this speed will be vary with respect to time and with respect to positions. Is that clear? The difference between the Eulerian description and Lagrangian descriptions. Overall, if I summarize this, Lagrangian description, we are focusing on a single particles. Eulerian description, we are not focusing on a single particle. We are focusing on what? Particular position, right? A finite control volume, a finite volume called control volume is defined through which the fluid in, whatever the fluid flow is there, will be going in and going out. We do not keep tracking of the what? Single individual fluid particle and its velocity of the what? Fluid particle or a fixed quantity. Rather than we are focusing our attention on what? At a fixed position. At this position, maybe number of particles, let them pass through that. But we are basically saying that what is the velocity at this point. So whatever the velocity we are writing as a function of x, y, z, and t, that is not the velocity of the single particle. That is the velocity of the complete particle at that location. Is that clear? Tell me guys. Or in a better sense, if I just give the example of city and we have the car in a city, individual car velocity is the Lagrangian descriptions. Whatever the individual car A velocity is there, velocity B, right? Velocity C. That means VA is nothing but the velocity of what? Car A, velocity of the car B, velocity of the car C. Individual car traveling history will be given by what? Lagrangian description. But if I say speed breaker 1 is having the speed 120 km per hour, more than that, no car can have the basically no car can exceed this particular limit. Speed breaker 2, 100 km per hour. That means all car has to be at this location, has to be 120 km per hour. That means if I say speed of speed breaker 1, that is given by Eulerian description. Right? That means it's a very awkward feeling that to say that, you know, we always say that what is the velocity of the ball? What is the velocity of the car? What is the velocity of the what? Right? What is the velocity of the car? What is the velocity of the what? Object. But Eulerian description saying that what is the velocity of the place? Place means that particular place in the fluid mechanics we define by particular point or a position in a control volume. Is that clear? Because if these things are not clarified, once we will be start our discussion on the what flow visualization techniques, you will be getting the difficulties there. All of you getting my point? Tell me, guys. That means in a Delhi city or in a Bangalore city, suppose, or maybe if I take the example of the Delhi city, right? What is the velocity of the car? That is a Lagrangian description. What is the velocity at the India gate? Velocity at the India gate at that location. Maybe infinite number of cars will pass through that India gate. But if I'll be asking you, what is the velocity at the India gate? That weird question will be answered by this particular person called mathematician called Eulerian. Right? Is that clear now? All of you. Fine. So these are the some important points regarding this, right? Because the infinite number of particles are there, tracing infinite particles, right, will take infinite amount of time, right? In laboratory, we have to view the results in a quick amount of time. We need not to do any kind of research there. Already so much of research has been done. Again, when you are doing the experimental kind of things, if you are taking too much of time, then there is no use of doing all the theoretical research, right? Now, note down, similarly, if you are studying the fluid kinematics, definitely fluid will be having some kind of what? Velocity, some kind of acceleration. Note down, acceleration field. Studying this acceleration field with respect, right? We don't bother about the individual tracing of particles, right? We don't bother about the where the particle A initially, now it is here, now at some point of time, what is the position of the particle? We are not bothering about that, right? We are just taking one camera and we are focusing our attention on particular position. That's it. Now in this acceleration field, acceleration of the particle, everybody know that acceleration is what? Dv by dt. Just like what we write velocity as what? Dx by dt. Similarly, acceleration can be written as dv by dt. But I told you velocity will be the function of what? X by t. I told you. Just see the example of the car. At this location, what is the velocity at the speed breaker 120? But this particular velocity is changing with respect to position or not? After traveling certain distance, the traffic signal 2 will be coming. Again, speed breaker 3 will be coming. So velocity will be the function of what? Positions x, y, z and t, right? Dv by dt. Now acceleration of the particle can be written as, now velocity vector can be written as u I cap plus v j cap plus omega k cap, right? How we are writing this one? My dear friend? We are writing like this. U v omega. U v omega, right? These are the velocity vectors in x direction, in the basically y direction, and in the z direction. Do not confuse. This is a complete vector. This is a small v. You can just represent it as small v, right? Make a note of it. In a vector calculus, right, in the particular mathematics subject, you will understand the vector calculus. Through the vector calculus, if you are representing this in a vector format, we can write like this. Acceleration can be written as, no need to worry, I will prove that. Dou v by dou t plus v dot del. Del is nothing but what? Del operator. This can be written as I cap dou by dou x, j cap dou by dou y, k cap dou by dou z. Anyone know about the delta operator, del operator? This thing you will study in the vector calculus. Any one of you know about this del operator? Tell me, guys. Perfect. Now, quickly just note down. So dv by dt can be written as dou v by dou t plus v dot del into v. My dear friend, the total acceleration we also call material acceleration. Total acceleration we also call material acceleration, right? It is divided into two components. One is a local acceleration, second will be convective acceleration or advective acceleration, right? Now, what is this? What is the meaning of, sir, advective or convective acceleration? And what is the meaning of local acceleration? That is what we have to study. While looking at the picture, this particular part of the component we call advective acceleration or convective acceleration. This part we are calling what? Local acceleration. So, what is the meaning of acceleration? Change in velocity with respect to time. Whenever the velocity changes are happening with respect to time, we call local acceleration. Whenever the velocity changes are happening with respect to space, with respect to position, due to the velocity changes with respect to change in position, change in space, that acceleration part will be called as advective acceleration or convective acceleration, right? Make a note of it, very, very important. Now, so particularly what we call in a Cartesian coordinate system, the component of acceleration can be written as ax, that is dou u by dou t, plus u into dou. How we are getting this one? That is what the, again, a good question. Now let me just prove this one. Now note on the equation ax, ay, and az. That means acceleration in the x direction, acceleration in the y direction, acceleration in the z directions, right? So these are the component of acceleration, right? So if you are writing total acceleration, then what we can write? Ax I cap, ay j cap, az k cap, right? If I just write the magnitude, ax square, ay square plus az square. But the main thing is that fundamental behind this particular formulas, right? Now, you know that velocity, when we write, the velocity is a basically function of coordinates x, y, and z, right? So just in a very quickly I will write. So what you can write, velocity u, total change in velocity u du. What you can write, total change in velocity du. What is the total change in x component of velocity? What we can write? By mathematics, by partial differentiation rule, we can write like this. We know that u is a function of what? U is a function of x, y, z, and t. At a particular position, remember, at a particular position, we are defining acceleration with respect to what? With respect to Eulerian description, not with respect to Lagrangian descriptions, right? Dou u by dou z into dz, dou u by dou t into dt. If I divide by dt, whole equation, what I will be getting? This thing will cancel out. Now, whatever the total change in velocity with respect to time in x direction will give the acceleration in x direction, no doubt about it. Now further, what will be having? Ax can be written as, what is dx by dt? Dx by dt, we know that it is u. Dx by dt is what? U. Dy by dt is what? V. Dz by dt is what? Omega, right? So what we can write? U into dou u by dou x, V into dou u by dou y, plus u into omega into what? Dou u by dou z, plus dou u by dou t. Similarly, my different ay can be written as dv by dt. So once again, what will be coming? Total differentiation of dv will be what? Dou u by dou x into dx. Dx divided by dt, again is what? U, plus v will be what? Dou u by dou y, plus omega into dou u by dou z, plus dou u by dou t. Az can be written as dou omega by dou t. Sorry, this can be written as what? D omega by dt, u into what? Dou omega by dou x, plus what we can write? v into dou omega by dou y plus omega into dou omega by dou z plus dou omega by dou t. Is that clear, all of you? Because see, d omega can be written as what? Once again, dou omega by dou x into dx plus dou omega by dou y into dy plus dou omega by what? Dou z into dz plus dou omega by dou t into dt. So if you just divide by dt, once again you will be getting the same thing. This thing will be what? This thing can be written as u. This thing can be written as what? Small v. And this thing will be what? Omega. All of you are getting my point? Is that clear? Acceleration in the Cartesian coordinate system? Tell me, guys. Any difficulty in this acceleration? Right. So if I write, see, this part of the component of acceleration will be called as convective acceleration or advective acceleration. Right. Now, if I write simple definition, the acceleration because of change in velocity, because change in velocity with respect to space, right? Acceleration because change in velocity with respect to space or position. What about this? This is nothing but local acceleration. Now, what is the definition of this local acceleration? The local acceleration is nothing but acceleration because change in velocity with respect to time. This is local acceleration. This is local acceleration, right? So these are the complete picture of Cartesian, basically what? Velocity in the Cartesian coordinate system, right? Acceleration in the Cartesian coordinate system. Now, once again, not only we have to study in this particular format, we have to study in a vector format also, right? In a vector format, what we can write? Understand very carefully. Acceleration in x direction, we are writing here, acceleration in the x direction, right? Here we are writing du by dt. This can be written as du by dt, right? What is this d by dt? Total derivative. Total derivative, right? Understand here. Here I am writing in which format? Here I am writing this one as vector v dot, that is a dot product of the complete velocity vector with the delta operator into u plus dou u by dou t. Because sometime in the gate examination they can ask, in particularly in the gate examination they can ask what? In a vector format, individual what? Acceleration component, right? Where delta can be written as I dou by dou x, j dou by dou y plus k cap dou by dou z. Now if you just multiply, what is the velocity? Ui plus vj plus omega k cap. If you just do the dot product, what you will be getting? Ui plus vj plus omega k into what? I dou by dou x plus j dou by dou y plus k cap dou by dou z plus dou u by dou t. So what you are writing, my different? You know that I dot I will be 1, right? J dot j will be what? 1. K dot k will be what? The dot product of the same vector will be what? What? 1 only. So u, what we can write? U into dou by dou x plus v into what? Dou by dou y plus omega into dou by dou z. These are the things will be there. That we need to multiply with the what? U. That we need to multiply with the what? U. Right? So what will be there? U into dou u by dou x plus dou u by dou t already there. Plus v into dou u by dou y plus omega into dou u by dou z plus dou u by dou t. And same expression you got in the before page like this. If you just compare exactly the same equation. but we have to write in the vector format. Similarly, what will be ay? That is dv by dt. Same thing, velocity vector v dot del into what? Small v plus dou v by dou t. Getting my point? All of your understanding in a vector format? Tell me, guys. Is that clear? Because when you multiply this term with this one, it will be coming here. Whatever the empty term is there, that will be fitted there. So that will become u into dou u by dou x plus v into dou u by dou y plus omega into dou u by dou z. These things will be more clear when you understand the mathematics about the vector calculus. Is that clear, all of you? Tell me, guys. Any difficulty in this part? Now, so these are the basically velocity vectors in the Cartesian system and acceleration ax, ay, and az in a particularly Cartesian coordinate system. Now, here you'll understand we can write the same whatever the acceleration is there, but in cylindrical coordinate system. In cylindrical coordinate system, what whatever the acceleration in x direction is there has to be replaced by acceleration in the radial direction, because in Cartesian system, what you have in Cartesian coordinate, you have x, y, and z. In cylindrical coordinate system, what you have, my different r, theta, and z. That means one will be radial direction, one will be angular direction, one will be what? Azimuthal directions, right? So ax will be ar, ay will be there. You can just think like a theta, and whatever the acceleration in z direction, that is, it will be same. R, theta, and what? Z. If you just write spherical coordinate system, again, that is not included in our particularly syllabus, but in that case, r, theta, and phi will be coming. In cylindrical coordinate system, it will be r, that is the radial direction, theta, angular direction, z, axial directions, right? Now, 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 try understanding what I'm just saying. In cylindrical coordinate system, what will be the acceleration in the radial direction? Total change in velocity, whatever the velocity component is there in the radial direction, the total change with respect to time, right? That thing we are writing minus v theta square divided by r, something like this. Only you have to remember ar. No need to remember this one, a theta and az. No need to remember. Only for gate examination, if I say ar will be more than sufficient, right? If at all the question will be coming on this cylindrical coordinate system, then you can write, you can just remember about this ar formula, right? Now, what is a VR? Radial velocity. The radial velocity can be written as dr by dt. What about v theta? R into d theta by dt, right? Hello, hello. All of you can hear me, right? Yes. So these are the cylindrical coordinate system. All of you have noted down this VR, V theta, and VZ. All of you have noted down. Now, here, so I told you, right, we have to remember only AR. No need to remember the formula regarding the A theta and AZ. You can see very easily that it is a very lengthy formula, right? So now, so we'll be solving some numericals. Here now, when you see this one, this particular question that has been asked in GATE 2017, an idealized velocity field is given as idealized velocity field P is given as 40x I cap minus 2t square y j cap plus 4x z k cap. This is the idealized one ideal velocity field that is being given at a point minus 1 1 0 and time t equal to 1 second. What they are asking, they are asking the magnitude of the material acceleration, right? So how to find that? Material acceleration magnitude they are asking, that means what? Ax square plus ay square plus az square. Now, for finding the material acceleration or total acceleration, what we have to do? We have to find the ax. How to find the ax? How to find the ax? Ax, we know the formula, right? U into dou u by dou x plus v into dou u by dou y plus omega into dou u by what? Dou z plus dou u by dou t. See, there is a very simple trick I will tell, right? After solving this particular problem, to remember the ax, ay, and az, right? Now, how to calculate the dou u by dou x? So in this one, this is the u component. So if I write here, what is the u? The u component of velocity is what? 40x. What is the dou u by dou x? When you do the partial differentiation of any particularly variable, which is a function of more than one variable, you have to keep one variable as a fixed one, right? And other with respect to other variable, we have to differentiate. Dou u by dou x means what? 4t, because dou x by dou x will be 1, right? What is the velocity component in z direction? V, that is minus 2t square into y, right? Now, if I just do dou v by dou x, then what will be the answer? 0, right? There is a no x component. When there is a no x component, that will be 0. What about dou u by dou y? So can we write minus 2t square? What is the dou omega by, sorry, dou v by dou z? What is the dou v by dou z? Once again, we don't have anything that is a z variable in the what? J component of velocity. So once again, it will be 0. What about dou u by dou y? What about dou u by dou y? Tell me, guys. Any y component is there? No, right? That is 0. What about dou u by dou z? Once again, that is 0. So dou u by dou z is 0. Dou u by dou y is also 0. So what we can write? U is what? 40x. Dou u by dou x is what? 40. What about dou u by dou t? That is 4 into x, right? If I just do dou u by dou t, what you will be getting? 4 into x, right? So here, this is the acceleration in x direction. So what we can write further? Acceleration in x direction, that is minus 1, 1 and 0 at this particular point, and time t equal to 1 second. What you can write? 4 into 1, x is what? Minus 1, 4 into 1 plus 4 into what? Minus 1. So this is minus 16 minus 4, that is what? Minus 20. This is the unit. What is the acceleration in the y direction? Tell me. What will be the acceleration in the y direction? what will be the acceleration, my different, in the y directions? So we can write what? It's a very simple formula. Y is there, you just write dou v by dou x, dou v by dou y, dou v by dou z, dou v by dou t. Now u v omega, that will be coming. U v omega, that will be coming. Similarly, x is there, so u will be there. Dou u by dou x, dou u by dou y, dou u by dou z. And similarly, u v omega will be multiplied. Plus this local acceleration will be there, right? So here what we can write, dou v by dou x is what? 0. What about dou v by dou y? Small v, we know that minus 2t square into y, right? And what about dou v by dou y? That is minus 2t square. Dou v by dou z, once again 0. What about dou v by dou t? What about dou v by dou t, my dear friend? Minus 4t into y. So minus 4t into y. So now if you write ay in at the particular location minus 1, 1, comma 0, and at time t equal to once again, so what we can write? This will be what? Y will be 1. Then it will be what? 4. Minus what? Y is 1, minus 4, t is 1. So that is 0. Look at very carefully. Acceleration in the y direction coming as what? 0. Right? So now if I just remove this part and if I just write omega component, that is a jet component of velocity. So when you write the jet component of velocity, what you can write? Omega. What is the omega? 4xz. So dou omega by dou x, once again this will be 4z. Dou omega by dou y, you can write what? 0. There is a no y component. Dou omega by dou z, that is 4x, and dou omega by dou t will be 0. So my different acceleration in the z direction will be what? Acceleration in the z direction we can write dou omega by dou x, dou omega by dou y, dou omega by dou z, dou omega by dou t. Plus I told you need to multiply with the what? U v omega. Plus acceleration in the z direction will be, see, dou omega by dou x, what we have along with the u, 40x, dou omega by dou x, that is 4z, dou omega by dou y, that is 0, dou omega by dou t, that is 0, omega into dou omega by dou z. So what we can write? Omega is what? 4xz into dou omega by dou z, that is 4x. So what we can write? Now when you consider z, this is a z, right? So when you just calculate at minus 1 comma 1 comma 0 and time t equal to once again, what you are observing that z will be 0, that is 0 plus 0, that will be 0. So overall acceleration part, if you just consider, this will be 0, this will be 0. So whole complete acceleration you are having, the complete acceleration you are having only with respect to what? X direction only. And now when you take the magnitude, you will be having the answer as 20. Is that clear, all of you? Tell me, guys. Any difficulties in this numerical? Yes. Is it clear? Correct. For all of you. Now, moving on to the next, this particular question, what you're looking right now. In a steady flow through the nozzle, the velocity on the velocity on the nozzle axis is given as u, that is given as what? U is equal to u naught 1 plus 3x by L. 1 plus 3x by L, where x is nothing but the distance along the axis of the nozzle from inlet plane and L is nothing but the length of the nozzle. They are asking what is the time required for the fluid particle on the axis to travel from inlet to exit plane of the nozzle, right? So here, if I just consider one nozzle, so this is my nozzle. The purpose of the nozzle is what? To increase the velocity and to decrease the pressure. So what you are observing that we are taking the, at this location, they have given the velocity in the form of u naught plus 1 u naught into 1 plus 3x by L. Now, while looking at the what you call only velocity component u, you can clearly tell that it is a unidirectional flow. It is a unidirectional flow. Only I component of velocity is given, not v, no component in the z directions, right? Now, when you know u, you also know that u is what? Dx by dt. So what we can write? U naught 1 plus 3x by L. So what we can write? Dx divided by u naught 1 plus 3x by L, that is equal to dt. So what we can do, we can just do the integration from 0 to L, so that we will be getting time. So what is the time? 1 upon u naught already there, that is a constant. So 1 upon something. So what we can write? Integration of 1 upon 1 plus 3x by L into dx. What we can write? You can consider this term as, suppose let 1 plus 3x by L, you can assume that z. So 3 by L into dx, what you can write? Dz. So now when you replace this one, 1 upon z into what? Dx, what you can write? Dx, dz into L by 3. Dz into L by 3. So 1 upon z, what is the integration of 1 upon z? That is a log z, right? Divided into what? L by 3. So same thing you can write here. L of z. Z is what? 1 plus 3x by L divided by what? We can write 3 by L. So finally, what is the total time required for the fluid particles to travel from inlet plane to exit plane? The total time required will be what? T will be what? L by 3 u naught ln of 1 plus 3x by L, right? But here we have to keep the integration limit from 0 to L. 0 to L. The length is what? Length of the nozzle they have given L, right? 0 to L. So what is the total time? L divided by 3 u naught ln of, when you put L limit, what you will be getting? This is not 4, this is L, right? This is L. So this will become what? 3 into L by L. 1 plus 3, that is 4, minus log 1, because x will be 0. So log 1 will be 0. So finally, what is the answer? L divided by 3 u naught ln of what? 4. B will be correct. All of you are getting my point or not? So can I say this is somewhat like a Lagrangian description? Or still we call this to be a Eulerian description? Tell me, guys. What is your observations? This, whatever the fluid velocity is given, is that the single fluid particle velocity or for the multiple fluid particle velocity? Anything you are getting? Any guessing? That is, once again, that will be what? Eulerian descriptions only, right? Because in the, yeah, correct. Because in the Lagrangian descriptions, you will be required the history of the particle. That means x will be the function of what? It will be the function of x naught, y naught, z naught, and t. That means you require from inlet plane, what is the history of the particle to travel from here to inlet plane? Once again, it is to keep on traveling to the exit plane, right? So maybe you will be getting one big function when you do the particularly Lagrangian analysis. You may not be getting a very simple velocity formula like this. You may be getting a one big particularly formula where the velocity can be written as in the function of what? U naught, that is x naught, y naught, z naught, and t, right? That means once again it is containing the initial position, and it will be containing the position or at this particular instant also, right? So in the Lagrangian, we have to trace the particle from the initial position x naught, y naught, z naught to some interval of time or whatever the instant of time. But in Eulerian, we don't bother about the history of the particle. We just say at a particular location, at this location and at this location, what is my particle velocity? That's it. And that is not the single fluid particle velocity, that is for multiple particle that is being passing through this position. So you can note down in the particular bracket along with this numerical that it is a once again Eulerian model, right? Now, because why I'm forcing too much on this Lagrangian and Eulerian description, because in GATE 2018 they asked for 2 marks. A very simple problem, just on the basis of categories only, categorizing this description, they ask for 2 marks, right? So at any time for the aerospace also, they can ask this particular in the fluid kinematics segment. Now, next thing we have to study about the flow patterns and flow visualizations. Now, what do you understand by the flow patterns or flow visualizations, or I would say, what do you mean by these streamlines? Anybody know? Streamline, path line, streak line. Now, in this particular segment, we have to study how the flow has been happening in a particularly flow field, right? So one basically to visualize, to basically see that how the motion of the particles are happening, what are all the tracing of the particle in a particularly velocity field or maybe pressure field, right? Suppose one aeroplane is there, for example, I'm just taking one example, and now aeroplane is moving in a particularly sky. So as an engineer, aerospace engineer, what you will be calculating, that what is the velocity field, what is the pressure field, right? At the end of the results, when you are doing the simulation, what you will be plotting the graph, what is the pressure field, what is the velocity field, right? That is a basic parameter, right? For a simple problem, I would say, for a 2D problem, not for the 3D flow, for the 2D flow, what you will be plotting, you will be plotting the pressure field, velocity field. The moment we are saying field, that means a control volume, that means Eulerian descriptions. That is a very fundamental thing. When you go for the any MTech interview also, they will be, suppose whether you mention or not aerodynamics, they will be asking this question. As an aerospace engineer, what you will be plotting the results, right? The pressure field and the velocity field. The next moment this question will be there, whatever the result you are plotting, that is based on the Lagrangian descriptions or Eulerian descriptions, right? And in that they will be keep on digging the questions, right? So first thing we are going to study about the streamlines. Now in this streamlines, once again I'm telling you that we are studying based on the Eulerian descriptions, Eulerian based. Now here what we are analyzing, what do you mean by the streamline? Streamline is a imaginary curve, that is not the real curve, that is the first thing, that is just there for the flow visualizations, right? Now streamline means suppose any curve is there, for example these are the curve in a flow field, right? In this curve you draw any tangent to this curve. Suppose at this point P, if I draw the tangent, right, at this point P2 you draw the tangent, or maybe at this particular point P3 you draw the tangent, for example. By drawing the tangent, what you are understanding, what you are getting, you will be getting instantaneous what direction of local velocity, right? So what they have written is streamline is a curve that is everywhere tangent to the instantaneous local velocity vector. You just take the any curve, you draw the tangent, you will be getting one what velocity vector, the direction of the velocity. Now you might be thinking, sir, what is the physical significance of this streamline? Is that the simple random imaginary curve, or it is having some physical significance? Yes, it is a very, very significant in analyzing the what, whenever the flow has been separated from the device, or maybe any recirculating flow, or whenever the separation of the fluid flow will be there from the solid wall, those cases can be easily identified by the patterns of the streamlines, right? That means, for example, here I would say, suppose you are just taking one example of diffuser. So when you just consider one diffuser, what is the purpose of the diffuser? Anyone know? Anyone know the purpose of diffuser? It is used in the engines, right? Tell me guys. Whenever the flow is happening through this diffuser, what is happening? The velocity will be decreasing and the pressure will be what? Increasing. Correct? Yes or no? So in this one, what you are understanding? You are understanding through this diffuser section, the velocity will be decreasing, the pressure will be increasing. The velocity will be decreasing, the pressure will be increasing in such a way that, suppose the flow is happening through this diffuser, but after some point of time you will be soon going to know that the velocity, whatever the flow field is there, that has been recirculated. The flow might be separated off from the wall. Now a very basic question is there. Suppose you have the convergence section or you have the divergence section, right? So whenever you observe that the whatever the shocking phenomena is happening, that is being happening in the what? Divergence section, not in the what? Convergence section, right? In the divergence section, what is happening? There may be chances of separation of the fluid is so high. The chances that the fluid may be getting separated from the solid wall is high, such a way that the whatever the shocking phenomena is there, that is being happening in the divergence section. Now once again, this whatever the flow field initially it is flowing like this, right? What you are observing, this is a diffuser, and through this diffuser, what you are understanding, the pattern of the streamline like this. The pattern of the streamlines, you are understanding that this is the pattern of the streamlines. Suddenly what you are understanding, the pattern of the streamline has been like this. But how can you so sure about that? Because when you draw the tangent, to this streamlines, you will be getting the what? Location of the direction of the what? The direction of the velocity vector. And by with the help of pattern of the streamlines, you will come to know that the flow has been separated. Why? Because initially the velocity vector is what? In x direction. But suddenly you are observing that the velocity has been what? Reverse. You are increasing, keep on increasing the diameter in such a way that the pressure is so high. Now the flow has been taking place from what? Right to left. Instead of, see, initially the flow is happening like this, but suddenly the flow is happening what? In a reverse manner. How? And how you are identifying that the flow has been reversed? Just with the help of pattern of these streamlines, right? So streamlines are useful as the indicators of instantaneous direction of the fluid motion throughout the flow field, right? It is being used basically, for example, in the region of recirculating flow and the separation of a fluid flow of a solid ball. Whatever the solid ball is there, that can be easily identified by the pattern of streamlines. Is that clear, all of you? Tell me guys. This shocking phenomena and all you will understand in other subject, but the basic fundamental idea I want to say that what you can get the idea by the drawing these streamlines, or whatever the streamline, whatever the results of the streamline pattern is there, that will be telling you what, right? Yes or no guys? Is that clear about the streamline, all of you? Now we have to understand the equation of streamlines, right? Equation of streamline. Before understanding the equation of streamline, one important note is there. Whether two streamline can ever intersect. Whether two streamlines, suppose this is one streamline and there is a second streamline. Can this two streamline, this is a streamline 1 and this is a streamline 2. Can these two streamline ever intersect? Tell me, guys. Intersection of the two streamlines are not possible because at the intersection point, when you draw the tangent, I told you, right? What is the purpose of the streamline? You draw the streamline, you take the tangent, the whatever the tangent direction is there, that will be the direction of velocity vector. But suddenly at the intersection point, for the same fluid particle, right? What you are understanding, when you draw the tangent, you will be getting another velocity vector, v1 and v2, right? Velocity is what? Vector quantity, right? It will be having both magnitude and single directions. When you are saying vector, what is the meaning of vector? It is having single magnitude, single direction, but you are observing that it is behaving like what? Not like a vector, right? That means it is going to have the two different directions, right? Suppose you are taking the admission into the school and you will be having the only single name, right? Your mark sheet also you will be containing single name. You will not be having the different names. So how the single fluid particles can have the two different directions? So that is not possible, right? So you can just note down two streamlines can never intersect. That is the first thing, first note. Second, single streamline, can the particularly a given streamline intersect itself? That means a single streamline is there like this. Single streamline is there, but can it basically cross itself? That is again not possible because at the intersection point, you will be having once again the two direction of the velocity, right? Third point, I would like to tell that third note point, and that is a very important. Understand what I'm saying. Note 3. At the stagnation point, right? At the stagnation point, suppose you have the flow field, one solid wall is there, and the flow is happening around this wall. Suddenly, what you're observing that it is being striking. At the striking point, the velocity component will be 0, x, y, and z. At the stagnation point, where the net velocity is 0, and remember one more thing, streamline, when you draw the tangent, it will give the instantaneous local velocity vector. That means it will give the direction of net velocity, right? Streamline gives the direction of net velocity. This word is very, very important. Net velocity. That means whatever the flow will be happening, that will be tangent to the streamline. That means suppose you have the two streamline, 1 and 2, the flow will be happening along the tangent to the streamline. No flow can take place perpendicular to this streamline. There will be not a single flow will be happening across these two streamlines. Why? Because net velocity is here. Net velocity in the normal direction is 0, right? So what is the discharge formula? Area into velocity. So in the normal direction, if you want to calculate the discharge, A into Vn, that is 0. So discharge will be 0. In the perpendicular to the what? Whatever the perpendicular to the tangent directions. That means across the streamline, flow is not possible. These are the few important points that is being asked in the GATE examinations, right? So at this stagnation point where the net velocity is 0, that means U component is 0, V component is 0, omega component is 0. At that particular point, we cannot define this streamline, right? Now, note down the equation of streamline. Suppose this is blue color, whatever is going here, this blue color line, this is one streamline, for example, right? At this streamline, you are taking one point P1, which is having the coordinates X and Y, as you can see. After a certain point of time, the particle position is P2, for example. The particle position is what? P2, for example. So this, on this streamline, if I draw by the black color, see here, this is P1, here this is P2, right? So this small gap, I'm just defining by dr, that is a position vector. What is the position vector? Dx I cap plus dy j cap plus dz k cap. In this small interval between the particle position V1 and V2, my dear friend, what you are observing, the particle has traveled from here to here. That is a dr distance has been traveled. This position vector in a basically in a space, I would define by position vector as dx I cap, dy j cap, and dz k cap, right? So what we can write? This velocity, what you are observing, that is being tangent to this by the definition of this streamline. When you draw the tangent, it will give the direction of velocity vector. This v and this dr is almost parallel with each other, right? This dr, if you just neglect this small angle, this dr and this velocity v is what? Parallel to each other. And we know that from the basic vector, whenever the two vectors are parallel, their cross product will be 0. So what we can write? Dr cross v will be 0. So what we can write? Dr is what? Dx, dy, dz. V can be written as u, v, omega. This will be 0. If we are keeping this thing as 0, then what we can write? If you are writing what? Dr cross v is 0, then what we can write? Here we can write, we just write I cap. I cap can be written as what? Omega into dy minus v into dz. Minus j cap will be what? Omega into dx minus u into dz. Plus k cap can be written as what? V into dx minus u into dy. That is 0 means what? 0 I cap plus 0 j cap plus 0 k cap. That can be written like this. That means what we can write? This term will be 0, this term will be 0, and this term will also be 0. So if I just say here, now what you're understanding? If I just say omega dy minus v dz is 0, that means what we can write? Dy by dz can be written as v by omega, right? Further, omega dx or w dx minus u dy u dz is equal to 0. So we can write dx by dz can be written as what? U by omega, right? V dx minus u dy, that will also be 0. So dx by dy can be written as u by v. So what you are understanding, my dear friend? Here dx by u, that is equal to dz by omega. Here dx by u, that is equal to dy by v. So overall, what you can write? Overall, you can write this one. This is the equation of streamline. Make a note of it. This will be the equation of streamline. Some of the things will be clarified when you know a little bit about the mathematics, about the matrix, how to find the determinant of the matrix. This thing, once it is clarified, then the technical subject will be very easily you can understand. The fundamental of the whatever the mathematics will be involved in the fluid mechanics, you can easily identify. Is that clear, all of you? Tell me, guys. Is that clear, all of you? Now, so here one more term is there, that is nothing but the stream tube. Now, what you are understanding by the stream tube? A stream tube is nothing just like a whatever the communication cable is there, right? The cable is, when you just open the cable, it will be made up of so many wires. Single wire, you can just think of streamline. So the combination of this streamline will give rise to one tube structure, tube kind of structure. That tube will be called as stream tube. Make a note of it. A stream tube consists of a bundle of streamline. It is much like a communication cable, consists of bundle of fiber optic cables, right? These fiber optic cables can be we can think it of as streamline, single streamline. So when you just make it, because see, we are drawing in a board, whatever the laptop screen is there, you can see only 2D view, right? So in a space that will be 3D, right? So you'll not be having a single streamline or maybe multiple streamline, right? Suppose the flow is happening through a nozzle. You don't find in a 2D figure. When you just combine this in a 3D figure, you'll be having one tube kind of structure. That is a stream tube, right? So in reality, stream tube is there rather than single or multiple streamlines. Now, the next thing will be the path line. So my definition, it is based on the name itself is very much clear. By the name itself is it is very much clear that it is based on the Lagrangian approach, right? So only one time, this is the time you are studying about the Lagrangian description. Except this, in whole fluid mechanics, we'll be discovering this. What? We'll be basically having the discussion on based on what? Eulerian descriptions only. It is based on the Lagrangian approach, right? Path line is nothing but, first of all, it is a real line. It is not the imaginary line, right? Now, path line is nothing but the actual path that is being traveled by individual fluid particle over some time period, right? Suppose a particle is there which is being traveling from here to here, right? This particle, suppose that means I would say you are taking one what camera, right? And you are making suppose the video of particle at time t equal to 0, at time t equal to 1 second, 2 second, 3 second, 4 hour, at the time t equal to t and second, what is the position of the particle? This path, when you basically trace it, right? This path will give the history of the single fluid part, individual fluid particles over some time period. That line will be called as what? Path line. Here, few observations are there. Single path line or individual path lines can intersect itself. Suppose path line is there like this, it can travel, 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 it can go like this, right? So single path lines, a path line, a path line can intersect itself. Why? Because it is not giving any direction of velocity vector, right, at the intersection point, right? So these are the few points that is a very important, because now the complete game is there on MSQ in gate examinations. The rank will be decided whether you are getting 170 rank or maybe you are getting 10 rank. That difference will be created by MSQ only. That's why they introduce MSQ. So be careful about the theoretical question also. So path line is the actual path that is being traveled by the individual fluid particles over some time period. And important observation that we can write, that is note number 1, a path line can intersect itself. Right? Second thing, it is there for single fluid particle. It is for single fluid particle. Now, particle is starting from 0 second and it is being traveled here time t equal to tn. The next most important thing is streak lines. First, we will understand what is the definition of the streak line. A streak line is the locus of the fluid particles. It is a locus of the fluid particles that have passed sequentially through a prescribed point in the flow field. Now, some of you, by the definition, I know that it is not very much clear. Let me explain the diagram so that you can easily identify what is a streak line. Now, what is a streak line? Before understanding this streak line, let me give an example. Suppose there is a one channel section through which one converging portion is there, which is being attached to this pipe flow, and maybe we are having numerous amount of fluid particles inside that, right? And all the injections are happening through this small point here, point P. Through this point P, all the injection of the fluid particles will be happening in a flow field, right? Now, so what we are going to cover here, suppose I'm just taking 4 particle. For example, I'm taking 4 particle. So particle 1 will be here, 2, 3, 4. Infinite particles are there. To explain you very clearly about this streak line, I'm taking 4 particles. Don't think that I can count the particle also. No. Infinite billions particles are there. Millions particle will be there. But to explain you the meaning of streak line, I'm taking 4 fluid particles. Right? Now, particle number 1, whatever the particle 1 is there, suppose it is being injected, right? And the particle 1 has been traveled, for example, like this. The particle 1 has traveled, the path line of the particle is like this, right? By making the video of the particle, we can trace the path of the particle that is being traveled. This is the path line of particle 1, right? This is the path line of particle 1. What about the second particle? The second particle is also being injected. And what is the path which is being traveled by second fluid particle? The second fluid particle, for example, this may travel like this. Path line of particle 2. Path line of particle 2. Third fluid particles which is being injected, they may follow like this. This will be the path line of third particle. What about the fourth particle which is being injected? The fourth particle will be, for example, here. Particle 4. Now, individual fluid particle we have drawn very carefully. Now try to understand, if I'll be asking you, what is the location of fluid particle at time t equal to 4 hours? At time t equal to 4 hours, initially I have injected at the time t equal to 0 hours, right? At the initial position, initial time is what? On the watch is 0. For example, reference, and whatever the reference time is there, I'm taking 0 second or 0 hours. And after 4 hours, I'm asking, what is the position of the particle? You will say the position of the particle number 1 is here. Particle 1 is here. Once again, you will say the particle number 2 is here. At time t equal to 4 hours, right? Particle 3 will be here, for example, you will say. Particle 4s are here, right? So what the streak line will say, that streak line will say, you just draw the locus of all the fluid particles at the particular instant from the starting point. From the starting point, whatever the position is there, so let me draw that. So whatever the position I have drawn here, whatever the location is there, all the local point I have drawn at t equal to 4 hours, but that is not the streak line which you are looking right now, the black color. We have to join it by the initial point. So this will give you a streak line at time t equal to 4 hours. If I'll be asking you what is the position of the particle, what is the position of the particle at time t equal to 6 hours, then it may be somewhere here, it may be here, it may be here, it may be here, right? So we can draw all the particle position from here to here, but we have to connect it with the starting point. So this red color is what? A streak line at time t equal to 6 hours, right? So once again, it is the Eulerian descriptions which is giving you the location of all the fluid particles which are there at the certain instant of time. It is just like taking the picture, you know. Suppose you have the camera, you have the video, you have made the video with the help of camera. by drawing the individual particle position. That is nothing but the trace of what? Individual particle, that is a path line. But at the certain instant of time, if I just ask you to take the snapshot, then what you will say? Whatever the snapshot you will take at this 4 hours, that will give you the local location of all the fluid particles at time t equal to 4 hours. And when you join together by from all the local all the position of particles at that instant of time with respect to initial points, that line will give you the streak line. Is that clear, all of you? Tell me this. Is that clear? Streak line, streamline, and the path lines. What is the physical significance of this streamline? Sir, it is just giving me the instant direction of whatever the fluid particle velocity. Path line, it is the history of the path line that is being traced, right? Streak line, that is the location of the fluid particle, all the fluid particles which is being prescribed in the flow field at the particular instant of time, right? That is a very simple terms, this streamline, path line, and streak lines. In a steady flow, for the steady flow, when the flow field is not being changing with respect to time, right? In that particularly flow field case, all the streamline, streak line, and the path line will be same. But for the unsteady flow, this all will be different, right? So make a note of it. So here, whatever the example you are looking right now, they have drawn the streak line by the green color, right? Some of you might be thinking, sir, how it is that possible? Yes, it is very much possible. How it is possible? Just think of this situation. Maybe individual particle is there. Particle 1 is here. Particle 2 is here. Particle 3 is here. Particle 4 is here. Particle 5th, 6th, 7th, and 8th. First of all, particle 1, that will be what? Injected, right? This particle 1 will be injected. Let's suppose the particle 1, the path line of the particle 1 is here, like this. Whatever the particle number 2 is there, let's suppose the path of the particle is 2 is what? Somewhat like this. So, particle number 3, for example, it will be like this. Particle 4, it may be like this, right? Particle 7, 6, 7, and 8, it will be like this, right? So these are the path lines of individual what? Particles. This is the path line for particle 1. This is the path line for particle 2. So individual path line is there, but this green color line, whatever we have drawn, this is the streak line at time t equal to capital T hours. Maybe they may be at this position. Coincidentally, no, fortunately, all are lying on the same, basically what? This location of the particles are such a symmetrical locations that when you draw from the initial point, it is basically like this, right? Individual path can be different, but the location, whatever the green color is there, whatever the green color is there, yes. So whatever the green color is there, that is being telling you the streak line at time t equal to capital T hours, right? So altogether, I want to conclude that a streak line is the location of or the locus of all the particles that have passed sequentially through a prescribed point in the flow field, right? Here you will be having some important points. If the flow is unsteady, the surrounding velocity field will be changes, right? What is the meaning of this? See, suppose you have the pattern of the streamline, right? Streamline 1, 2, 3, and 4. In a particularly flow field, suppose the flow is happening like this, right? So if you draw the tangent, it will be pattern of the streamline. That is what I have drawn. But suppose the flow field is unsteady, right? At time t equal to 1 second, the particle is traveling like this. The next moment, the particle is traveling like this. The particle is traveling like this, suppose with the velocity v2, initially velocity is v1. The moment velocity will be changing, the pattern of the streamline will also change. Because tangent will give the velocity vector, right? Which tangent? Streamline. So once the pattern of the streamline will change, the path line, streak line, and streamline will all together will change. So if the flow is unsteady, the surrounding velocity field changes, and we cannot expect the resulting streak line to resemble a streamline or path line at any given instant of time. However, if the flow is steady, all the three lines will be identical. Second point is streamline represent the instantaneous flow patterns at a given instant of time. I told you, right? At time t1, suppose flow field is what? Is steady. That means velocity will not change with respect to time. That means what? Velocity will not change means what? Either magnitude or direction, both are not changing. That means magnitude is not changing. Okay. Direction is also not changing. That means same streamline. The pattern of this streamline will what? Indicated by what? That means what? Whatever the streamline is there that represent the instantaneous flow patterns. A streak line is an instantaneous snapshot of a time integrated flow patterns. A path line is nothing but what? A path line is a time exposed flow path of an individual particle over some time period. Right? So streamline and streak lines are what? Eulerian descriptions, and you can just think path line as with respect to what? Lagrangian descriptions. Is that clear, all of you? Is that clear? Tell me, guys. With respect to this, whatever the discussion happened just now, based on this, if you solve this one question they have asked, theoretical question in 2014, to observe the unsteady. First of all, unsteady is there, right? Unsteady separated flow. So by the name itself, whenever the separation is there, the separation is a highly unsteady phenomena, and you can observe very clearly that it is being happening in the divergent portion. Some of the flow field has been separated off from the solid wall because pressure might be so high that it is going to reverse its direction, right? Now, whatever the fluid particles are there, they have been replaced by the bubbles by giving the name bubbles. These bubbles are being injected at 10 microsecond interval at point A, right? This bubble acts as a tracer particle and follow the flow faithfully. The curved line AV, which is being drawn at any instant, represent what? A option is not possible because it is an unsteady flow. In an steady flow, whatever the streamline, streak line, and the path lines, they cannot be have the same what representations. They cannot be same, right? In an unsteady flow, a streamline and a streak line and the path lines will be different. Now the question will be whether it is a streamline or path line, or only streak line. Tell me, guys. So it is just like what the example we have discussed just now, So injection of particles may be happening, for example, maybe we are start injecting like this. Example 1, 2, 3, 4, 5. Particle 1 injected, it has been travel like this. So location of the particle may be here. Particle 2, it may be here. Particle 3, it may be here. Particle 4, it may be here. Particle 5. So, but whatever the black color is there, this line is there, this represents the location of all the fluid particles at instant time, right? At time t. So this obviously will represent the streak line. D option is correct, right? This cannot be the path line. That is not the telling you the location of single particle. That is being telling you the location of multiple fluid particle. 1, 2, 3, 4, 5. Right? Is that clear, all of you? Whether it is clear? Now, now you try to solve this numerical. The fluid flow is being represented by the velocity field. This velocity field they have represented like ax I cap plus ay j cap, where we can write the complete velocity field as u I cap plus small v j cap, where u component of velocity, that means it is a 2D flow, right? X is there and y component is there. U is what? Ax Small v is what? Ay. So here, my dear friend, they are writing what is the equation of a streamline passing through a point 1, 2. So what is the equation of a streamline? Equation of a streamline, we know that dx by u, dy by v. So dx by u, what is the u? Ax. Dy by v, ay. So what we can write? Dx by x, dy by y. So further what we can write? If we just do the integration, what we will be getting? So log x is equal to what? Log y plus some constant of integration will be coming, right? So this constant of integration we can write log x is equal to log y. We can write log c dash, no problem. Once again, log c dash will be c. Once again, that is constant, right? X can be written as c dash into y. How to find c dash? So they have given that at x equal to 1 and y equal to 2, right? When x equal to 1, c dash will be what? 1 upon 2. So what we can write? X is equal to 1 upon 2 into y. So 2x minus y will be 0. So which option is correct? C will be correct, right? Is that clear, all of you? Equation of streamline. Is it clear? Now, I think all of you noted down, right? Here, when you just consider the second question, consider the following statement regarding the streamline. What is the first statement they are mentioning about the streamline? It is a continuous line, right? Yes, it is not a discontinuous line. It is a continuous line, such that when you draw tangent, when you draw the tangent, to this streamline, not exactly like this. When you just draw the tangent, it will give the, it will show the what? Velocity vector at that point. Vector means what? Magnitude directions. It will not give the reading of magnitude. It will give the reading of what? Instantaneous directions, right? And I told you there is a no flow across this streamline. No flow can be taking place like this. All the flow must be taking place tangentially, right? Second statement is also correct. First is also correct. Third, what they are saying, dx by u, dy by v, dz by w is the differential equation of the streamline. Yes, correct. Now, by looking at the option, what is the, which option is correct? D. Now think of this fourth option. In an unsteady flow, the path of the particle is a streamline. Once again, it is wrong, because for unsteady flow, streamline will not be equal to path line, will not be equal to streak line, right? There's no any permutation combination that, sir, in an unsteady flow, streamline path line will be equal. Maybe streamline and streak lines are not equal. It is not like that. In an unsteady flow, path of the particle is not a streamline. So fourth option is incorrect. Getting my point, all of you? Tell me, guys. Because in the tangential direction, it is giving you the net velocity. What is the meaning of net velocity? The complete velocity in the tangential direction. Then what is the component of velocity in the perpendicular direction? Zero, right? Suppose if I will say that the velocity having the vector like this, one will be tangential, one will be normal. Suppose v1 is there, v2 is there, this is the v net, under root of v1 square plus v2 square. But when whole velocity v1 is the become net velocity, then what is the v2? Automatically zero. The same phenomena is here. And that is what this statement number 2. There is a no flow is possible across these two streamlines. Is that clear, all of you? Tell me, guys. Clear? All of you. Any difficulties? Now we have some more basically terms and terminologies like what is a vorticity, what is a circulation, what is the angular deformations, what is the linear deformations in the fluid particles. But as basically we have the time constraint, so we are not discussing that part. We'll be moving on to the next topic, that is the mass conservations. We also call continuity equations, right? So how many of you are aware of this equation, continuity equation? Tell me guys. So while looking at this conservation of mass, in a shorter format, we say continuity equation. Very first thing is that before starting our discussion, I would like to ask you, what is the physical significance of studying this conservation of mass? Tell me guys, what is the physical significance of studying this topic? Anyone know? Yes. So conservation of mass, basically it gives you the validity of fluid mechanics. Whenever you are studying any aerodynamic subject, remember that conservation of mass will always be satisfied. Getting my point? Tell me guys, mass will always be conserved, whenever any flow field is happening, mass cannot be go anywhere, right? Earth cannot take whatever, the sky cannot take the whatever the mass is there which is being flowing through a channel section, right? It has to be conserved, right? So validity of the fluid mechanics, will be given by this conservation of mass. Very small, very quickly we will discuss the equation and we will solve one numericals which is being asked this year only, right? So try understanding what is the conservation of mass, right? Suppose you have, I will be explaining through one bank example, right? For example, you have the control volume like this. Once again, we are studying what? Eulerian description, right? We are deciding to select the control volume. That means we are focusing our attention on a fixed space, right? We are not focusing our attention on single particle, right? Right. Now, suppose this is a bank, for example. Suppose you have deposited some amount. For example, you in a particular bank, you have deposited some amount and you have withdrawal, right? Suppose you have deposited 100 rupees, for example, right? And you are withdrawing 50 rupees. But after some point of time, what you are observing that you have some extra amount. You should have only 50 rupees, right? 100 rupees incoming, 50 rupees, whatever it is going out. So 50 rupees has to be there. But what you are observing with respect to time, you have some interest, right? Obviously that will be in the form of interest. You will be getting what? More amount. There's no doubt about it. Further, what is happening? This interest we are writing what? If we just convert rupees in terms of mass flow rate, so what we can write? 100 rupees, that is mass that is being coming in, dou by dou t of whatever the with respect to this mass in a control volume, whatever the mass changes are happening with respect to time in a control volume. That means whatever the changes are happening in a money with respect to time, that is giving you in the form of what? One interest, right? So that is dou m by dou t in a control volume plus mass flow rate that is being going out. If it is a steady flow, then what you can write? For the steady flow, what you can write, my dear friend? If I just say for a steady flow, whatever the incoming is there, that is outgoing. No storage. If there is no storage, no changes with respect to money. Suppose you have deposited 100 rupees and suppose one day, day number 1, you have deposited. Day number 2, you have withdrawn completely 100 rupees. No amount you are being leaving to the bank account. That means what? No interest will be there. So what we can write, dou m by dou t in the control volume, that will be 0. So what you can write for the steady flow? Steady flow, you can write summation of mass flow rate in, that is equal to summation of mass flow rate going out. Right? Suppose you have only single account, single input section. Sometime we may have multiple account, multiple input section also, right? Depending on the control volume, depending on the device. Make a note of it. Now let me explain you the, see, we can derive the equation of conservation of mass by considering Eulerian description. There is no problem in that, but that will take some time. In our full particularly course, we will be deriving with respect to what? Eulerian description. We have the less amount of time now, so I will be deriving based on the Lagrangian descriptions. Very easily you can derive, right? Whatever the Lagrangian, that means we are considering one solid object. You think of fluid particle as solid object, right? And we're gonna say that whatever the mass is there, that is what is the volume into density, right? What we are writing? See, Lagrangian description. So by Lagrangian system, Lagrangian, it has been focused his attention on a fixed mass, right? He has been focused his attention on a fixed mass. Single mass. What is the mass? M. What is that? Volume into density, right? Take the log on both the sides. So log M equal to log V plus log rho. Now differentiate with respect to time. Differentiate with respect to time. So what we will be getting? 1 upon M dm by dt, 1 upon V dv by dt, 1 upon rho d rho by dt. This thing we can write. My dear friend, you know that a mass, a fixed mass, will not change its mass with respect to time. Dm by dt will be 0. Yes or no, guys? Particularly, you have the mass, right? In your particular, you have body, you have the weight. With respect to time, the total mass of the body will what? Will not change. With respect to time, it will be same, right? So what we can write? 1 upon V dv by dt, 1 upon rho d rho by dt will be 0. Right? So further what we can write? This dv by dt, 1 upon V dv by dt, what we can write? Change in volume by original volume, right? Change in volume dv by dt 1 upon V, right? So we are writing this as volumetric strain rate. What we are writing? Volumetric strain rate. No need to worry. We will be studying the linear strain rate, what are the angular strain rate, and what are the volumetric strain rate. What are the volumetric strain rate? The volumetric strain rate, we are writing this as volumetric strain rate. This is nothing but summation of strain in x direction, strain in y direction, strain in z directions. We can also write this as dou u by dou x plus dou v by dou y plus dou omega by dou z. Right? So further what we can write? If you write here 1 upon V dv by dt, that is a volumetric flow rate, right? So this we can write dou u by dou x plus dou v by dou y plus dou omega by dou z into rho plus d rho by dt. Complete d rho, what we can write? Once again, the rule of partial differentiation, dou rho by dou x into dx plus dou rho by dou y into dy plus dou rho by dou z into dz plus dou rho by dou t into dt. Divide by dt, divided by dt, divided by dt. So what we'll be getting? So you will be getting here, this term will be u, this term will be small v, this term will be small omega, that is a w, this term will be 1. So here complete equation if I write, so rho into dou u by dou x plus dou v by dou y plus dou omega by dou z plus what we can write u into dou rho by dou x plus v into dou rho by dou y plus omega into dou rho by dou z plus dou rho by dou t, that is equal to 0. That is equal to 0, right? So after this one last equation is there, then we can solve the numerical, then we can close the session. Now understand, whatever the equation we have written, this is the equation number 1. Let's suppose this is the first equation, right? This is nothing but complete equation for 3D flow. We can also call this to be a continuity equation. A continuity equation, 3D general continuity equation. What we can write? It is just like a 3D general continuity equation, right? So further we can simplify, right, by writing into the format. So whatever the equation here you have written for incompressible fluid or for incompressible flow, for incompressible flow of incompressible fluid, what we can write? Rho will be constant. The rho will be constant means what? What you can write, my different? Once the rho will be constant, whatever the rho is there, if it is constant, then dou rho by dou x will be 0. Automatically dou rho by dou y will be 0. Dou rho by dou z will be 0. And dou rho by dou t will be 0. All the things will be 0. Then you will be having with this equation dou u by dou x plus dou u by dou y plus dou omega by dou z equal to 0. Rho cannot be 0. So this term will be 0. So what you can write? Dou u by dou x plus dou u by dou y plus dou omega by dou x, dou z will be 0. This is the 3D continuity equation, 3-dimensional continuity equation, 3-dimensional continuity equation for incompressible flow. Right? Make a note of it. On the basis of not this, usually the student used to remember this final equation. No, you have to remember the full equation, this one. That is a very special case where you have the special case. Of course, we have many special case, but such a special case number 1 we are discussing for the incompressible flow where rho is constant. And remember, it is valid for both steady flow and unsteady flow. That means with the help of only condition of incompressible flow, you can never judge whether it is a steady flow or unsteady flow. That means, what is the meaning of this? Whatever the equation is there, if you say what is steady flow, unsteady flow. For example, if you say unsteady flow, if you just say unsteady flow means what will happen? Tell me, guys. Or whatever the, if you say steady flow means what? If density will be constant, whether dou rho by dou t automatically 0 or not? Tell me, guys. If density will be constant means what? Suppose you have given in a flow field density as what? 1000 kilogram per meter cube for water. That is not going to vary with respect to time. Automatically it is 0. So whether you are mentioning about the steady flow or unsteady flow, that will not be the matter of concern for us, because that density term will be gone. Getting my point? Velocity may be the function of time. I'm not saying the velocity is not the function of time. For unsteady flow, velocity may be the function of time, but density will not be there. In a continuity equation, we are not getting dou u by dou t, we are getting dou rho by dou t. Remember that, right? Now, on the basis of equation number 1, we have one this year only in GATE mechanical, one question. Just think of this equation. Consider a unidirectional flow field. The flow field is given as velocity u of x and t, x, y, z and t, which is given as u of x and t I cap. That means it is a one directional flow. It is a one directional flow and it is a function of only x and t, right? And one condition is given at x equal to 0 and time t equal to 1, maybe 1 unit. They have not mentioned anything about the second, so I'm just mentioning about the unit. At t equal to 1 unit, they have given that the velocity is what? They have given the velocity as 1. if the spatially homogeneous density field is also varies with respect to time 1 plus zero point 0.2 e to the power minus t. They are asking what is the value of the velocity at 2 1, right? Now, so what equation we have to use it? So we have to use full equation, that is rho into dou u by dou x plus dou v by dou y plus dou omega by dou z plus what we have to use u into dou rho by dou x plus v into dou rho by dou y plus omega into dou rho by dou z plus dou rho by dou t, that is equal to 0. Now they have not given anything about the z component or k component. So v will be 0, omega will be 0. So directly v will be 0, omega will be 0, right? And dou omega by dou z automatically 0. This will also be 0. So what we will be getting? Dou u by dou x plus dou rho by dou t, that is equal to 0. So rho is what? 1 plus zero point 0.2 e to the power minus t, that is dou u by dou x plus dou rho by dou t. If you just do the differentiation, what you will be getting? E to the power minus t minus 1, that is equal to 0. So finally dou u by dou x, what you will be getting? Dou u by dou x you will be getting as 0.2 e to the power minus t divided by 1 plus 0.2 e to the power minus t, right? This is the particularly equation you are getting. Whenever we do the integration, remember, in case of total differentiation, in case of total differentiation, when you do the integration, one constant term will be coming. But in case of partial differentiation, in case of partial differentiation, what you will be getting, my different? In case of partial differentiation, when you do the integration, remember, constant term will not be there. It will be some function. That means when we write u 0.2 into e to the power minus t 1 plus 0.2 e to the power minus t into x plus some function of t, because automatically when you do the differentiation, once again dou u by dou x, this term will be gone. But don't write as a constant, that is a blunder, right? You just write as a function of t. So what you can write? U, how to find f of t? Initial condition at time t equal to basically what? T, it is not t, it is 1. At time t equal to 1, right? And when x is 0, you have 1, right? So 0.2 e to the power 0, e to the power what? When x is 0, so this all term will be gone. When x is 0, so f of t is what? F of t, you are getting one constant, that is equal to 1. So once we know the f of t, we can put into that, that is u is equal to what? 0.2 e to the power minus t divided by 1 plus 0.2 e to the power minus t plus 1. Now we know the function u, we can directly put what we need to find? U at x equal to 2 and t equal to 1. So when you put into that, e to the power what? Minus 1 plus 1, right? Into x is also there. Combination of what? X is there. If you just notice here, x is there, right? So we have to write x. Here we can write the black, that is x plus 1. X is what? 2 plus 1. So what is the u? When you just calculate, you will be getting 1.137 approximately. This will be the answer. So this year they have tested not only the general 3D continuity equation, they have tested the whether you know the full continuity equation or not, mass conservation equation or not. Is that clear, all of you? Tell me, guys. Any doubt? Okay. Okay, thank you all.